So let's start off looking at elements. The formulas of composition. So we're looking at the elements in chapter 6 nomenclature. Most elements like, for example, if we had gold, you know, the name is gold, but the formula is not gold. G. A lot of people will think the formula is G for gold or GO, but it's not. G, is there an element G? Ga is gallium. But is there an element with just G? No. How about GO? No. There's no, and so it makes sense that they would use GO, but it's not GO. What is it? AU. And there's a reason for that. It's from Orium. Orium is another name for gold. It's like sodium. You know, I asked, what's the formula for sodium? A lot of people, not a lot, but some people in Chem 4 will write SO. Seems to make sense because SO is not taken by anything. S is sulfur. Se is selenium. And so Sc is scandium. So it just makes sense that sodium would be SO. But it's not. Yeah. It's not, because if you look at a package of salt, you know, what it lists the ingredients, and the ingredients is written as NaCl. Na. But there's a difference, because gold, you can have a small piece of gold, or you can have a large piece of gold. Is there a fixed size of gold? Is there a distinct unit or entity of gold that we have? So, for example, water, you know, is it possible to drink a half a water molecule? No. You could have one water molecule or two water molecules, or any multiple of that, but you can't. So for gold, is a big gold crystal made up of a distinct smaller gold crystal? You know, the smallest gold crystal is this. And we could have one gold crystal, two gold crystals, but we can't have 1.5 gold crystals. Is that possible? No, it turns out we can have any size piece of gold we want, from big to small. And so there's no discrete unit. Some things form a discrete unit. Water would be one of those things that form a discrete unit. Actually, did I finish water last time? Or was I still working on water? I don't remember. We were talking about the number of water molecules. There are 9 water molecules. I think we finished that, right? Okay. We talked about the average mass, the atomic mass. Okay. Average weight. Good. And so something like gold, you know, I don't know how many isotopes there are of gold. Now that, it would be nice to be able to predict how many isotopes of gold there are, but what would you need in order to make a prediction like that? Yeah, a lot of gold to observe it, but, you know, we need a lot of gold, but predicting is different than measuring. You know, for predicting, we would need 0 gold, because we just do this mentally, you know? And in order to do that, we would need some kind of model, and a very good detailed model that has widespread acceptance that allows you to make predictions is called a theory. Yeah. So we need to understand the theory. Well, that theory is not in the realm of chemistry. That theory is in the realm of physics. Yeah, or nuclear chemists, or nuclear physicists, or nuclear chemists. Yeah. And so they'd be worried about that. What we do is just feed it into mass spectrometer and then determine, you know, there are this many peaks, therefore this many isotopes, and how much they weigh. But for us, okay, gold is going to form some kind of crystal of gold. But what we're going to do is, it depends on how big the chunk is. Do you want to count how many atoms of gold there are and call that gold 1,600,000, etc.? No. What we do is we break it down into the simplest unit. The simplest unit of gold is just a single gold atom. And so we represent that as AU. This is the simplest unit of gold. And we call that the empirical unit. Empirical has two definitions that we deal with. So this is called the empirical unit. The two definitions of empirical are the simplest unit, like a single atom of gold, like that. And then we could build up a crystal of gold by taking a simplest unit and adding a bunch more. What's the other definition of empirical?
Isn't it a conclusion? It's like verified through the scientific method. The conclusion verified by the scientific method.
Kind of. It's not really the conclusion. It's kind of like the midway point. Like empirical law. Have you heard of an empirical law or an empirical equation, mathematical equation? What does that refer to? An empirical law or empirical equation versus a theoretical law or theoretical equation. I know it's a long time ago we talked about this. And time, your memory fades rapidly. Pretty rapidly. So you have to kind of refresh your memory. The same thing happens to me all the time. I took a memory class. This is one of these online things that was well recorded. But it was the world record holder for memory. And one of the things he said was he memorized the entire periodic table. That was one of the early things that he did. He didn't memorize the entire periodic table. You know what he memorized? He memorized all the elements, their names, the symbols, and their number. So he knew all the numbers. But I thought, that's not so useful because that's like just raw observation. It's much more useful. If he said he had memorized the periodic table, I would have been much more impressed. But all he did was he memorized the number and the element and the name, of course, the symbol and the name. And so, like, for example, you give him a number, he'll tell you what the element is. But could he tell you what position, what family it's in? That he didn't say. So I assume he didn't memorize that. But, that would have been a heck of a lot more useful if you could memorize that. But anyway, this chapter is tons of memorization here. This chapter is tons of memorization. So do you want to memorize all this the night before the test? Some people do that. Maybe they have photographic memory. If you have photographic memory, then maybe you can do that one night, memorize it all. Other people will require more. Me, I require a lot more time to memorize it. But even memorizing it, okay, we memorize the raw data. But, if you memorize the raw data, don't you want patterns? Isn't that better? Because if you memorize just the raw data, then you can't predict things, right? If we have at least a pattern, we can make predictions. So empirical equations are kind of the midway mark. Empirical laws are the midway because we can make predictions based on the pattern alone, but not based on theory, not based on a deeper understanding, but just based on pattern. We do a lot of that here in this particular chapter. We learn the pattern, and once we learn the pattern, then we don't have to memorize as much because we can predict things based on the pattern, simple pattern. Well, anyway, getting back to this, it would be nice to know the other definition of empirical. The other definition of empirical would be, and it should have been quick, based on observation. And this definition of empirical means the simplest unit. So the two common definitions of empirical. Well, the simplest unit is not always an atom. So if we have gold, the simplest unit would be like that. Sometimes it's a little bit tricky because gold usually forms only one crystal structure, but something like carbon is a bit more tricky because carbon has different forms. Actually, there are a bunch of different forms. We have diamond. That's one form of carbon. You know another form of carbon?
Graphite.
Graphite. And a bunch of others. Graphene. Buckyballs. You heard of those? Mm-hmm. Buckyballs. Tubes. So many different forms. Amorphous, etc. And so they're just a bunch of them. And so how do we differentiate these? Well, diamond has a different kind of structure. This is what we call metallic lattice here. And it forms a crystal. Diamond also forms a lattice. So this is also a lattice, but it's not a metallic lattice because carbon's not a metal. Now, the metals are on the left side of the periodic table. Carbon's kind of in the middle, right? And so this is different. We call this a covalent lattice. We'll talk about that later, but this forms another lattice. Graphite has a different kind of lattice as well. Or it just extends on. It's also a lattice structure. When we have the lattice structure, we have different simplest units. Like the simplest unit of this, diamond, we just usually use a carbon atom. And so the simplest unit of diamond would just be a single carbon atom because you have small diamonds and big diamonds. You know, are all diamonds the same size? No. Are big diamonds made up of little diamonds? In a way, yeah, in a way, no. There's something called the unit cell. The unit cell would be the simplest representation of this structure. The structure of diamonds is different than the structure of graphite, so they're going to have different unit cells. But we aren't going to get that far. All we're going to say is if we have diamond, we're just going to break it down and call it carbon diamond. This is to represent that it has a different structure than carbon graphite, which has a different structure than graphene, which forms these graphite-like sheets, etc. That would be empirical unit. But something like sulfur is a bit different. There are two common forms of sulfur. There's something that we have called yellow sulfur. Yellow sulfur forms discrete units. You know, if I look at a diamond lattice, it just keeps going on and on. Same thing with the graphite lattice. But for sulfur, we get sulfurs linked together, but it's fixed at 8 members like this. And so this is a sulfur forming a ring of sulfur atoms, and it's always 8. Like, when you try to stick a 9th in there, it doesn't seem to work, or 7, it doesn't seem to work. It's just always 8 for some reason. It forms a structure with 8 sulfurs. And so what happens is if I have a big sample, a big crystal of sulfur, if I have a big crystal of yellow sulfur, you know, I was looking at this thing, you know, and it's pretty impressive. You know, they have these people go into these volcanoes or volcanic, and then they gather sulfur crystals from them. It's a harsh environment. It's hot, and the air has lots of other gases. oxides of sulfur and other things. But if I have a big crystal of sulfur, a big crystal of sulfur consists of lots of these rings put together. Not put together, this is stacked one on top of each other. And so this forms a discrete unit. The discrete unit is called a molecule, and this would be the simplest unit. And so the simplest unit, the empirical unit of this is S. Well, actually, this gets tricky because since it forms molecules, the simplest unit of yellow sulfur is S8. And so this is yellow sulfur. We also have white sulfur. There are others, but white sulfur just has a chain of these. These chains are what we call polymeric chains. And there's no beginning, no end. You know, they can be giant or they can be small, you know, depending on how many sulfurs you put in this chain. Whereas these rings only form 8 for some reason. These chains can form 8, 9, 10, 11, 12, any number of sulfur atoms in this chain. And so when we have something like this, where the chain length will vary, and then what we're going to do is we're just going to use the empirical unit of this. The empirical unit, the simplest unit, would just be S. And so even though we could call this a molecule because they're all linked together like this, we're just going to call it S. This is solid. This is also solid over here. These are solid as well. So some things like to link up. Well, most things like to link up. In fact, most things will link up. And they'll link up into a lattice or into molecules like this. And so, for example, phosphorus. Now, when we have different forms, you know, like, for example, diamond graphite, yellow sulfur, white sulfur, all these are called allotropes. Allotropes are different structures of an element. Phosphorus has 2 common allotropes. There's red phosphorus. In red phosphorus, the phosphorus atoms are just linked up like this. And you can link a bunch of them together or just a few of them together. And so there's no distinct beginning, no distinct end. They just keep going. Kind of like the polymeric chain of sulfur, but there's more cross branching here. The structure is a little bit more complex. So if we're dealing with red phosphorus, then the simplest thing, since there's no discrete unit, we just call it P. You know, you can call P red, but this P is solid, let's say. Then we have white phosphorus. White phosphorus forms these cages. These cages are going to have 4 atoms like this, linked together, bonded together. And so this is the smallest unit of white phosphorus that we're going to get, and it's the molecule. A molecule is a discrete unit. This is the smallest unit we're going to get. And so if we had a crystal of white phosphorus, we'd have a whole bunch of these cages stacked one on top of each other to form that. And so we call this P4 solid. It's white. So most elements, we just use the empirical unit. They form some sort of lattice or polymeric type structure. But some of them we don't, like yellow sulfur and white phosphorus. Those are two that we don't typically. There are some elements that don't like to link up with any other atoms. Like gold likes to link up with gold. All these atoms like to link up with other atoms, but the noble gases don't like to link up. And so these are atomic. So for example, if I have helium, they don't want to come together and bond together like all these other ones. Helium just likes to be alone. So this is atomic helium. So helium, helium, helium. They stay apart from each other. You can force them together by cooling them down. You know, you have to cool it down to 4 Kelvin, get them to liquefy.
At that point, it's a superfluid, right?
Helium? Actually, I'm not sure. That's a superfluid or not. Liquid helium. Superfluids would be defined by what characteristics? You know, if you define a superfluid, what would it have?
Close to zero viscosity. Or
Close to zero viscosity. Helium has probably close to zero viscosity. Helium is used in electromagnets, liquid helium. You know. So I used to use liquid helium quite a lot. It's hard to see because it vaporizes so fast. But anyway, this likes to be alone. All the other noble gases, all the other members of the family, neon likes to be alone, argon, krypton, xenon, all these like to be alone. They don't like to bond to each other. So it's easy. Helium, the formula for helium is just He. It doesn't form molecules. These are atomic elements. But we also have diatomic elements. Diatomic like to link up with one other. So, for example, hydrogen doesn't like to be alone. So when we look at hydrogen gas versus helium gas, hydrogen gas likes to bond together to form a molecule. And so this would be a discrete unit. And that would be a gas here. There are 7 diatomics that you should memorize. Hydrogen's 1. What are the others? Helium? Well, helium's just solo. Helium, argon, krypton. Those are solo. Yeah. That was good. Let's take a look at the periodic table here. Although this periodic table is in Chinese, I think. I like the numbering system here that they have. I was trying to get a periodic table. Our book's periodic table doesn't come up on e-version. I have no idea why it didn't come up. That periodic table may be hard to see. So hydrogen, and then these, the halogens, we call this is the halogen family, but also nitrogen, oxygen, do as well. Well, that's hydrogen. And then we have nitrogen. That likes to pair up. So this is nitrogen, the element, which we call N2. If air is made up of nitrogen, is it N or N2? It's N2. If air contains oxygen, is it O or O2? It's O2. So oxygen is going to be O2. What do you think? Is oxygen bigger or smaller than nitrogen?
big, smaller.
Yeah, it makes sense. Smaller is correct, but why is it smaller? Because shouldn't it be bigger? Nitrogen has 7 protons, and can you guess how many neutrons it should have? You know, of course we don't want to guess. Of course we'd like to predict how many neutrons it has, but in order to predict how many neutrons it has, we need to know all the isotopes of nitrogen. Do you know all the isotopes of nitrogen? No. Mm-mm. But we do know the average mass of all the isotopes of nitrogen. And the average mass, if you can read it here, it's probably hard to read, but it's 14.007, which means that on average, how many neutrons are there? 7. So 7 plus 7 is 14, and the mass number and the mass are about the same. So yeah, it looks around 7. In fact, it's probably the most abundant. Should be. Oxygen has 8 protons, and then look at the mass, 15.999, which means that probably it's going to have about how many? It should have about 8 neutrons. That gives us oxygen 16, and oxygen 16 turns out to be the most abundant isotope. Could you tell there's an oxygen 17 and an oxygen 18? No. But we know it's got to be around 8 because it adds up, right? And so it has 8 protons, 8 neutrons, and 8 electrons. Nitrogen has 7 protons, 7 neutrons, and 7 electrons. So oxygen has more stuff, more subatomic particles. So it having more subatomic particles should be bigger or should be smaller? It should be bigger. But that's not what's observed. What's observed is oxygen is just slightly smaller than nitrogen.
Is it just denser?
It would be denser, that's correct. But what's the hypothesis? You know, this is the observation. What's the hypothesis? We don't have the hypothesis now, but there's going to be a hypothesis. Do you know what it is? Yeah, right. Because more protons means that it's like a tractor beam, you know, in sci-fi. It's going to pull the electrons in closer. And so fluorine has even more protons, 9 protons now. And fluorine, 9 protons is a stronger kind of tractor beam for the charge. It pulls it in. And so that's 9 protons. How many protons does chlorine have? Chlorine has 17 protons. So chlorine should be minuscule, like really, really tiny. Right? But is it? Actually, chlorine is bigger than all these. So we have to think, at least we have to hypothesize, why is chlorine bigger than all those? We don't have to hypothesize now, but
uneven distribution of the attraction.
No, the traction is still operational. It's still functioning as predicted. Oh, let me get. Yeah, another ring or another shell of electrons. We're going to talk about this later. We don't have enough theory to answer this anyway. These are just observations. What do you think? Okay, bromine's bigger. What do you think about iodine? Bromine, chlorine, fluorine, chlorine, bromine, iodine. Iodine should be bigger yet. So if I compare bromine, iodine, make it bigger down here. I ran out of room. If I were to compare in terms of reactivity, you know, I told you about my iodine gargle. Did I tell you about that? And the iodine nasal aspiration? Mm-hmm. What if I ran out of iodine? Could I use bromine?
Yeah.
Yeah, except bromine is a bit more reactive. I could use bromine, but it hurt. Probably. And not only would it hurt, it probably caused damage. You know, damage that I don't want, damage to healthy. You know, is what I'm trying to do with the iodine. Do you know what I'm trying to do with iodine?
Oxidize the virus.
Yeah, oxidize. You know, because I'm trying to oxidize the bacteria and the viruses to kill them. That's what I'm trying to do. And bromine would be more effective because bromine, we say, is a more powerful oxidizer than iodine because of its smaller size. And bromine would be more effective at killing, but it would probably also cause damage that I don't want. You know, what would be even better? Chlorine. Did I tell you when when I was in the Boy Scouts? This is years and years ago. We brought bleach tablets. Have you heard of those? We put those in water. water tasted awful. But the water tasted awful, but it killed everything. We wanted to kill Giardia. You know, Giardia, you can get really sick from Giardia, which comes from feces that can contaminate water supplies. And so it was effective. Nobody got sick, but everybody got sick from drinking chlorine water. It tasted awful. Mm-hmm.
So is iodine the same as iodine?
Is iodine the same as iodine?
Medical grade iodine.
Yeah.
Okay, so if I were to take iodine, and I was allergic to iodine, would that kill her?
Yes.
Okay,
If you're allergic to iodine, don't take iodine.
No, she is, I'm not. But I was thinking about it because I do get sick very often.
Okay. Well, you know, I'm allergic to iodine. I'm allergic to iodine, yet I still do this. I'm allergic to, because have you ever gone for a CAT scan? If you go for a CAT scan, they give you imaging agent. So I've gone for multiple CAT scans. One CAT scan I had was I took a barium sulfate cocktail. It was like a pasty stuff. But the last CAT scan I had, they gave me iodine and drank it to image, like I had some stomach issue or something. I forgot what it was. So they used iodine. Then I had an allergic reaction to iodine. It was mild. But you know, with the providine iodine thing, I have no reaction to it. You know, it's mostly external. That wasn't taken internally. I don't drink the stuff. When I gargle, I spit it out. Yeah. When I pass it through the nose, I just spit it out also. If I drank it, then I'd probably have an allergic reaction. I remember in organic lab, one of the students got a drop of bromine. You know, they use bromine to oxidize some of the organic chemicals there as a test. Spilled just a tiny, tiny drop on their hand. They weren't wearing gloves. And then just wanted to call 911, get immediate medical treatment. But I was thinking, oh my gosh, you know, I'm drinking chlorine water. Come on. A little drop of bromine. It's overreaction.
Did they think they were allergic to it, or?
No, they're just scared because these are just powerful oxidizers. So they're just scared that they're going to have some non-allergic reaction. Maybe they're allergic. Then if they're allergic, then I would understand.
They use bromine as a substitute for chlorine in pools too, right?
Yeah.
At a certain, maybe their concentration that they're using is much higher.
Yeah, they use bromine, so you can do the bromine content of pools. But bromine has a kind of a bad environmental rap right now, you know. The bromine's present in fire retardant, and so you know the gymnasts have like I think 3 to 6 times the bromine level in blood than normal people. I just read that yesterday. I think that was. I didn't know, you know, if you're on the mats, you wouldn't think that, you know, you'd be absorbing that much of the fire retardant there. But that was kind of an interesting study. I wouldn't have thought of it. I mean, I guess this is kind of old news. I'm just behind in my reading. This is a study in 2013. But we have different forms of it, you know. So the fire retardant isn't bromine. Bromine's not going to act as a fire retardant. These are usually organobromine reagents, the fire retardants. And so it's what we call brominated flame retardant. It's like the chlorofluorocarbons. You know, chlorofluorocarbons are non-flammable. Did you know that? And so, but we could use bromine instead, because bromine in the same family as chlorine and fluorine. And so they're talking about it. What is it? The levels. Yeah, so quite high levels of bromine in their blood. Fluorine, if that was a drop of fluorine, you'd be very worried because the reactivity goes up. Fluorine is going to be the most reactive because of its small size. So, one of the things on the periodic table is this. The smaller the size, the more reactive. Except these helium, neon, argon, krypton, those like to be alone. They don't like to interact with anything. And so these are called the noble or the inert gases because they're so unreactive. But fluorine is super reactive. Neon doesn't want to react with anything. Chlorine's a little less, bromine's a little less, iodine's a lot less. And so it makes sense to have iodine. But it depends on the form, So iodine would work fine. I do the nasal and the gargling. But what if I ran out of iodine and I had iodide? I bought some iodide. Did I tell you I bought some iodide? After the Fukushima meltdown, I was thinking, since some radioactive fallout could make it to the U.S., I ended up buying some potassium iodide tablets. A lot of the iodide tablets sold out at the time, so I just bought some potassium iodide pure, or close to pure. And so they said, well, I'm sorry, we're out of potassium iodide because there's a huge run on iodide tablets after the meltdown. Did I tell you about in Europe after Chernobyl? The European countries that gave the children iodide tablets had much lower rates of cancer, thyroid cancer. So I had iodide. Would iodide work? So if I ran out of povidone iodine, could I use iodide to gargle and iodide? No, it's totally different. It's totally different because, when we think about oxidizers, and oxygen is the prototypical oxidizer, what do oxidizers want? What defines an oxidizer is oxidizers want electrons. And oxygen happens to want 2 electrons. Because if oxygen, normally oxygen has how many? 8 electrons. If it gains 2 electrons, how many electrons is it total? So 8 plus 2 gives us 10 electrons. 10 electrons is the same as neon. So there's something special about 10 electrons. In fact, there's something special about 2, 10, 18, 36, 54. All those are special numbers of electrons. And, when we have these special number of electrons, it makes things kind of stable. So oxygen wants 2 and then it stops. It doesn't want 3 because if it gets 11 electrons, it's not so beneficial. Fluorine really wants how many electrons? As many as it can get or just 1? Each fluorine atom just wants 1 electron. And so if I have 2 fluorine atoms, each one will take 1 electron. And if it takes 1 electron, then it has 10 electrons. And so you don't, to burn something, like in a flame, we have little holes in the burner here, and those holes allow oxygen to get in. The oxygen's from the air. But we don't need any oxygen. I could actually use fluorine instead. In fact, fluorine would burn more intensely because it's a more powerful oxidizer. So fluorine can do the same thing. It can take our methane and combust it. But we wouldn't form CO2. Do you know what we'd form? Close. I mean, that's good thinking like that. This is actually Chem 1A. This is a Chem 1A homework question. So if you burn methane in fluorine, do you know what you form? You don't form CO2.
Oh, you form an acid, yeah, chlorine hydride.
Close. You know what you form? You form carbon of fluoride. Rather than an oxide of carbon, we form a fluoride of carbon. We're going to learn how to predict this, but we're going to form this. We call it carbon tetrafluoride, which is a fluorocarbon. This stuff is the nerve. This is why they use it like in fire retardants, like these brominated, chlorinated, fluorinated things, because this is pretty stable now. It's a lot less reactive because now the fluorine's happy. Fluorine was terribly unhappy here. It wants an electron. Now what it does is it takes electrons from carbon. We'll talk about this in a few minutes. And so it's happy. And the other product of this is not H2O. You know what the other product of this is? HF. Now, how did I figure this out? I figured this out. One way you can figure it out is just memorize it. But, memorizing is not that great, It's much better to memorize a pattern. So, for example, the diatomics, I write it in this pattern. Why do I write it in this pattern?
It follows the shape of the periodic.
Yeah, it follows the shape of the periodic table. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine. So it's a lot easier to remember. And then hydrogen. Hydrogen's off to the side. But those are the diatomics. And so if I remember this little elbow here, that's a lot easier than memorizing these one by one. So if you memorize these with a flashcard, that's like just memorizing raw data. But we don't want to memorize lots of raw data. What we want to do is we want to take that raw data and refine it into a pattern, hopefully, and maybe a law. That would be great as well. So we have that pattern, and then what were the other two in the pattern? What were the other two that form molecules that are pretty common? The other two elements that form molecules that are pretty common. Not diatomics, just molecules in general. The only molecule carbon forms is buckyballs. And buckyballs originated in outer space, and then they made them in lab here. But you don't see them, except in meteorite impacts. You might see buckyballs that form on the Earth's surface.
Oxygen. Maybe sulfur?
Sulfur and phosphorus. So you see phosphorus and sulfur right here? So if you can kind of remember this pattern, then you kind of know. Everything else in the periodic table we represent by single atom. But these we're going to represent N2, O2, F2, Cl2, and then white phosphorus is P4, yellow sulfur is S8, and then those are the molecular. So if we know the pattern, then it helps us remember things a little easier here. So other alternatives is this. Yes, like bleach tablet. I could take bleach tablets or chlorine tablets and then gargle with that. It'd have to be lower concentration probably, but it would probably hurt. And this doesn't taste all that great either. But that would cause damage. But what if I ran out? And then could I take the iodide instead? And the answer is no, because iodide's not going to work, because iodine wants how many electrons? One. When iodine gains one electron, we call it iodide instead of iodine. And so iodide is like this. It gained that electron, and so we have I, which we call minus. And this is an ion. It has an extra electron. Does iodide want to gain more electrons? No, because it has 54. If it goes to 55, it's no longer good. And so iodide would be totally worthless to gargle, and nasal aspiration would be a waste. Just wasting iodide.
Iodide is clear.
Iodide is clear, colorless. Iodine is purple, red, orange, depending on how concentrated it is. However, when these are all these what they call the preppers websites, they're getting ready for a nuclear bomb or something like that. And so they ran out of iodide completely. And so on the sites, if you search, if you were looking for iodide at the time, Fukushima, there was none. In fact, even in Japan, they're saying, we have a limited supply of iodide, so we're not going to distribute any iodide. And so they didn't even give iodide to the children there. Unfortunately, the number of thyroid cancer cases is pretty high in Japan. But they said, well, one alternative is, since we're out of the iodide tablets, you can take iodine. That makes sense. You know why? Because if you drink iodine, it's going to oxidize the tissue around there and convert it into iodide. And then the iodide can get concentrated in your thyroid. And that would protect your thyroid. So in that case, it would work. And so it's really important what the charge on these is. That the charge is going to tell you the balance of protons and electrons. And that charge is really going to dictate this. Did I talk about the Dr. Jekyll and Mr. Hyde? Mm-hmm. Yeah, and so that's the same thing, as this, the charge. Now, on the right side of the periodic table, the smallest are the most reactive. But on the left side of the periodic table, they typically don't want to do that because, like say, oxygen wants to gain 2 here. It's 10 inches. Oxygen wants to gain 2 to become like neon, but let's go to something like sodium. How many would sodium have to gain? 7, because we have 11, so it'd have to gain 7, and then we're at argon. Argon's another noble gas, so it's got that number of electrons we'd like. But to gain 7 electrons, that would be pretty difficult. That's a lot of electrons to gain. So rather than gaining 7 electrons, you know what sodium's going to do? It's going to lose 1. If sodium loses 1, then it's going to have 10, just like neon. And then it's going to stop there. And so these ones, when we lose electrons, we call them reducers. So we have oxidizers on the right, and then we have reducers on the left. Now, one of the most powerful reducers is, do you know what one of the most powerful reducers is? Potassium? Potassium is very powerful, but what's even more powerful than potassium? It's either sodium or rubidium. So what would you predict? Rubidium. Why? Okay, and the reason is this. I'm going on a side topic here just for a second, but I want to talk about this. So sodium's pretty reactive. What's bigger, sodium or potassium? Potassium's even bigger. Even though it has more electrons, it's got more what we call shells. We'll talk about that later. So in sodium versus potassium, if they dumped potassium metal into Lake Lenoir in Washington, you would have seen even bigger explosions. It would have been pretty massive explosions there. And then rubidium is even bigger. But the biggest of them that's non-radioactive would be, what's the biggest of them that would be non-radioactive? Cesium. Cesium would be the biggest. Actually, francium should be bigger, but francium's radioactive. And so this is why everybody wants to see cesium react with water. When I was a student, they passed around an ampule of cesium in my advanced inorganic class. They said, I told you this, right? They said, don't drop it. If you drop it, it's going to react violently with the humidity in the air and cause an explosion. And so everybody was very careful with it because they didn't want to drop it.
Did you feel comfortable during not trusting your classmates not to drop it?
The ampule was pretty thick-walled, and even if somebody dropped it, it probably wouldn't have broken. It wasn't like fragile glass. It was thin-walled glass, then I'd be pretty nervous. But it was. I thought, well, if somebody dropped it, it's probably going to be okay. But no, you got to worry about that. So on this case, when we lose electrons, it's easier to lose electrons on a big atom because cesium wants to lose how many electrons? Only one. In fact, rubidium only wants to lose one, potassium only wants to lose one, and sodium only wants to lose one. So when we're losing electrons, the bigger, the better, the easier it is. And so cesium should be the most violent. When we're gaining electrons, when we're trying to take electrons away, the smaller, the better. So the most reactive on the right side are the smallest ones. The most reactive on the left side are the biggest ones. Now, do you want to memorize the size? I don't usually memorize the size. The size is easy to determine because I memorize the pattern. Do you see the pattern in the periodic table? Where's the smallest atoms located on the periodic table? Upper right. And the biggest atoms? Yeah, lower left. And so the biggest down here, francium, the smallest would be like helium up there. Although helium doesn't want any more electrons because it's full. It can't accommodate any more electrons. So then we know the patterns of reactivity of the elements here, which we'll talk about later again. In fact, we're going to revisit this shortly. It's gone. Nitrogen is not a very good oxidizer. Oxygen is pretty good. This is not balanced. Okay, so we talked about diatomic elements, and then atomic, molecular, lattice. It should be it. Let's talk about compounds next. The compounds are what? Compounds are two or more elements that are chemically combined in a fixed ratio. Chemically, what we say is chemically bonded in a fixed ratio. Versus mixtures. You know, in mixtures, the elements aren't necessarily bonded, although they could be in alloys. You know what alloys are?
Metals.
Yeah, metals. So, for example, 18 karat gold is what we call an alloy. It's not pure gold. In fact, if we look at all the gold atoms, once in a while we'll hit a different. This is like 75% gold atoms, and then we'll hit a silver atom in there. Substitute for a gold atom or others. And so in that sense, the silver is unbonded, but the key difference is it's not in a fixed ratio. You know, I can put as much silver and mix it in with the gold as I want. If I'm an unscrupulous dealer of 18 karat gold, I'll probably try to make it as much silver as possible, you know, because I can just increase that. Maybe rather than 75% gold, I can get away with 74.5%. But in a fixed ratio, we can't change that. So like water. So let's look at water, H2O. This is a compound, two or more elements, is chemically combined in a fixed ratio. So we have the law of multiple proportions. Law of multiple proportions says simple whole number ratios, and then we have the law of constant composition. The law of constant composition says that pure water anywhere in the universe is going to have the same constant composition. H2O. That's it. But we have others. You know, H2O is just one compound of hydrogen and oxygen. Can you think of another compound of hydrogen and oxygen? Hydrogen peroxide. Hydrogen peroxide has a formula H2O2. These are examples of molecular compounds. These are examples of what we call binary molecular. Here they form discrete molecules, compounds. And molecular compounds are compounds of non-metals, typically. Non-metals. Not always. It's not a law. It's just a rule. How about others? How about like, what else can you think of? How about H2O3? You think of that? Is it even a thing? Or H3O? How about that? Just throw in one more hydrogen in there. Is that a thing? No. Well, what are you going to do? Well, we can memorize them. Do you want to memorize all the compounds of hydrogen and oxygen? Or do you want to maybe try to look for some kind of pattern? You probably want some kind of pattern. It would be easier than memorizing every single compound of hydrogen and oxygen. And let me tell you what the pattern is. Even though the pattern's not really discussed here, we're going to use it later in the next chapter as well. And the pattern is going to do with something called oxidation state. And the oxidation state is what we call the apparent charge. And so hydrogen can do two things. If I look at hydrogen, hydrogen can gain one electron because hydrogen has one electron. If it gains one electron, then it goes to -1. I mean, actually, it goes to helium, right? And so it can gain one electron and be like helium, or it could actually lose one electron. If it loses one electron, then it's got no electrons, but that can happen as well. And so hydrogen's charge oxidation state varies from +1 to -1. That's what we expect for hydrogen, +1 to -1. Oxygen would like to do what? Oxygen would like to gain 2. If it gains 2, then it has extra electrons, not protons. It gets a charge. We call the charge 2-. So that means it has 2 extra electrons, 2 extra negative charges. And so this is common. But it could also do what? It could also lose how many? This wouldn't be likely, but it could also lose 6. Because if it loses 6, it's going to go to helium. If it gains 2, it goes to neon. Do you see that? That's called the oxidation state range. And so the range for this, in terms of apparent charge, is going to go from +6 to -2. And it could be somewhere in between there. So if we look at this, we're going to break it down into apparent charge. If oxygen got its way, how many electrons does it want? 2. And so what we're going to say is this oxygen gains 2 electrons and gives an apparent charge of -2. We have 2 hydrogens here. And this is a compound. Compounds are electrically neutral. Ions have a charge. Compounds have no charge. And so to make this electrically neutral, -2 plus 2 are going to balance out. And so the total positive charge must be +2. That total positive charge is distributed on both these hydrogens. So each hydrogen is plus. And so now oxygen's very happy, right? Oxygen's -2. Hydrogen's okay at plus. It's not going to be terribly sad. It's lost an electron. How about this one? Oxygen would like to gain 2. So I have 2 of them, so each oxygen wants to gain 2. That gives me a total of -4. I have 2 hydrogens here. That means each hydrogen, well, needs to add up to +4. So each hydrogen must be +2. Now, whether you call it +2 or 2 plus, they're kind of the same thing, but there's this convention people do. The number and then the charge. Sometimes you'll see that frequently. But there's a problem with hydrogen. How many electrons does hydrogen have? Hydrogen only has 1. How can it lose 2? And so that's an impossible charge for hydrogen. And so what that means is this is not possible. In fact, hydrogen can only lose 1. If hydrogen can only lose 1, then oxygen is not going to gain 2. Oxygen is only going to gain 1. And so this is wrong here. We're going to have to call this -1 or 1-. And so the charge on this oxygen is 1-. Well, is that going to make oxygen happy? No. Because oxygen really wants to gain 2, but it can't because there's not enough hydrogen. If there are more hydrogens around, then oxygen can take another one. But there's not enough hydrogen, too much oxygen. And so in this case, this one is going to lose 1. That means this oxygen is only going to gain 1. And so this ends up being a net charge of -2. This one ends up being a net charge of +2. So water we can drink. There's no problem with drinking water. But what if you run out of water? You know, we're in drought. And you have a bottle of hydrogen peroxide. You're really thirsty. Are you going to drink the bottle of hydrogen peroxide? No. Why? Because hydrogen, you can gargle. In fact, you know, the FLCC thing where I got gargling with iodine, they also have the instructions for gargling with hydrogen peroxide. So you can do nasal aspiration with hydrogen peroxide and gargle with hydrogen peroxide. I used to gargle hydrogen peroxide too. You know, when I was a student, I did this. I would gargle with hydrogen peroxide to prevent colds, so I wouldn't miss any class. I did that, and in fact, I stopped doing it. You know when I stopped doing it? I stopped doing it when they put a stabilizer in the hydrogen peroxide. So after they put the stabilizer in hydrogen peroxide, I couldn't gargle with it anymore because it tasted funny. Because I always had hydrogen peroxide around because I use hydrogen peroxide as an antiseptic. So if I got a cut. Now they don't recommend hydrogen peroxide anymore because it causes too much tissue damage. There's other problems having an oxidizer around. Betadine's better, you know, the propylene iodine, a little milder. But I could have used hydrogen peroxide because peroxide wants 2 and it only has 1.
Could you have H3O?
Could you have H3O? We're going to look at that next. Okay, but let me finish off with this. Do you understand why this is an oxidizer? This is an oxidizer because oxygen is unhappy. It just needs 1 more electron and then it's going to be happy. Okay, how about H3O? Would H3O, well, you can memorize it. Does H3O exist or doesn't exist? What would it be? Okay, here we'd have oxygen would be
2.
Yeah, 2-, and then we have 3 hydrogens. And those hydrogens would be, so this is going to be -2. These have to add up to +3. In order to, now, They don't have to add up to plus 3. These got to add up to plus 2. I can see how they could add up to plus 3, but how would this work?
Oh. Okay.
Yeah. This one has a problem. And this has got to equal 0. So what is each one? Now, we could have mixed charges. So maybe it's plus 1, and 0. That could happen. But in this case, why would that happen? And so H3O doesn't exist. However, H3O plus does exist. H3O plus is fine because oxygen is going to be wanting to gain 2. And then hydrogen can lose 1 so that the total is plus 3. So plus 3 minus 2 gives us plus 1. You see? And then we call this is called hydronium. Hydronium exists. So let's name these. This we don't expect exists. I could, it would just have something else to help it. You know what this is called? So when we name binary molecular compounds, this is binary molecular compounds. The rule is this. The first element, we leave the name alone, and then we use a prefix. 2 gets the prefix di. So this is called dihydrogen. Dihydrogen. And then we only have 1 oxygen here, so we call this dihydrogen monoxide. Dihydrogen monoxide is sometimes given the acronym DHMO. Okay, this would be called the systematic name for water. The systematic name is dihydrogen monoxide, or DHMO. The common name for water is just water. The common name for H2O2 is hydrogen peroxide. The systematic name would be dihydrogen dioxide. Dihydrogen dioxide. But nobody ever calls it dihydrogen monoxide. Have you ever heard it called dihydrogen monoxide?
No.
You have?
They just wanted to be really smart.
Oh, okay. Yeah, a lot of people do that. In fact, those smart people threw a prank on the city council. Do you hear about that?
I think so.
Yeah.
I think there's like hydrogen monoxide in the water.
Yeah, some activists convinced the city council to implement a ban on DHMO in the city. I think this is Lake Forest or one of these. It almost passed. The resolution almost passed, and so it's pretty funny, actually. But they're saying DHMO is potentially toxic. Too much DHMO, you could drown or something like that. Yeah. So that's pretty well known. But of course, water and hydrogen peroxide are the common names. But some things we don't have the common name. We just use the systematic name. So let's take a look at some things that we use a systematic name for. One of the things we use a systematic name for is this. You already know the name of this. What is the name of this? It's CO. It's a gas. It's a poisonous gas. Carbon monoxide. So in this, we name the element carbon, and for the second element, we change the ending. Rather than calling oxygen, we call it oxide. So we change the ending to "ide." And the same thing over there, oxide. We only have 1, so this is carbon, not oxide, but this would be carbon monoxide. Because there's another carbon oxide. Do you know what the other oxide of carbon is?
Carbon dioxide?
Carbon dioxide. So carbon dioxide would be the other. And this is also potentially toxic, but not nearly as toxic as carbon monoxide. And so there are different levels of toxicity in terms of this. CO2 is, there's plenty of CO2, nobody's necessarily dying from it here. But if you're on the space station, then you could potentially die from CO2. So what they have to do on the space station is they have to scrub the CO2 out of the air, otherwise the concentration of it builds too high. You know, but fortunately, there's no plants or trees on the space station. But you know, they're planting. You should plant more trees because the trees will take CO2 and use it for photosynthesis. So this one's called carbon dioxide. Di means two. How about carbon? What would this one be called? Yeah, this one would be called carbon trioxide. But, you know, I just need to unscrew the barrel a little bit more. Do you know what I mean by unscrew the barrel? Just need to unscrew the barrel of the burner a little bit more to get more oxygen in there. Once I get more oxygen in there, I should form carbon trioxide. True or false? False, because prove it to me.
Because carbon doesn't want to bond with that oxygen.
Why? I've seen carbon bond with that many oxygens. You know where I've seen carbon bond with that many oxygens? Geologists know this. Do you know what this is called? This is not a compound. You know what this is? This is called an ion. The difference between a compound and an ion is going to have a charge on it. A compound has no overall charge, no net charge. Geologists are very familiar with this because this is called carbonate ion. Limestone, calcite, you know, all those are carbonate. Marble is carbonate. And so I've seen carbon with 3 oxygens. Why can't I have carbon trioxide? Just unscrew the barrel a little bit more. Get a little bit more oxygen in there. Maybe get some carbon trioxide. Yes? No. One thing is you could just memorize it. The answer, you're right, the answer is no. Unless well, actually, I shouldn't say the answer is no, because there could be some exotic species like these, you know, these peroxide type species. You know, there's things like peroxide, and then there are a whole bunch of these. Have you heard of superoxide?
The other day when you brought it up.
Yeah, the other day when I brought it up. Superoxide and other things like this. Actually, the other day when I brought it up, I was trying to bring up this. Yeah, I found this, so where is it here? This is pretty interesting, although this is not the correct formula for superoxide, but this guy's an MD. This is that Dr. Schwelf. Dr. Schwelf has a website called MedCram. He's a professor of medicine at UC Riverside and I think Loma Linda. And the guy is board certified in 5 subspecialties of medicine, you know, which is a lot. So he has his MedCram. If you're interested in this, there's all these courses. Most of these are paid, but a lot of these are free.
Are these things we should worry about now or worry about closer to the end of
You don't have
undergraduate med
to
school?
worry about it at all. I mean, if you're headed this way, you know, or biology type applications. I set up an account. You can see some free stuff on here. Like he's been posting. He has like 200 videos on coronavirus, but he has a bunch of other videos too. He gives these updates on coronavirus. He has the hypothesis. You know, one of the things from the original strain of coronavirus was this thrombosis. You know the thrombosis? Have you heard of that? Thrombosis, blood clots. And what's the mechanism, you know, of blood clot formation? So this is his hypothesis on blood clot formation. I'm not gonna, if you watch this, then oh shoot, did I just? No, I just did that. Oh, you know what? You know, people say, "Oh, don't eat high fructose corn syrup," right? In these times of coronavirus, don't eat high fructose corn syrup. It's pretty interesting data here that they got on high fructose corn syrup, which surprised me because I eat high fructose corn syrup and I never thought much of it. But after watching this, I thought maybe I shouldn't eat high fructose corn syrup so much anymore. Because I used to like high fructose corn syrup because when I was in junior high, you know, one of my friends' mom made these Rice Krispie treats, so delicious. And I asked for the recipe. The recipe was lots of high fructose corn syrup. They're so good. But high fructose corn syrup can lead to a lot more thrombosis. Avoid that. Although I don't know about the new strain. New strain, you don't hear much thrombosis, right? I think. But this is the hypothesis. I wanted to show this because, you know, the difference between theory and hypothesis. You know, the other day I was watching this crime thing, potential crime. They don't know if it's a crime, but did you hear about this Kylie Rodney in Lake Tahoe went to a graduation party near Truckee, Nevada or something, and then disappeared?
I think so.
Yeah. There's a huge search, like huge search for her. And then they finally, this guy who has a YouTube channel who searches underwater wrecks, looks for people who crashed and found her. Actually, law enforcement didn't find her, but they found her car. It was in the lake, upside down. And so there are a whole bunch of theories going around, you know, was there foul play or was it an accident? But we don't call those, in science, we wouldn't use the term theory because the theory is very special. With a theory, you should be able to predict, you know. Theory has to meet certain criteria. And so really that's a misuse of the term theory in science, although some people still use theory to mean a hypothesis. What's the difference between a hypothesis and a theory?
I think the hypothesis is also individualized. It's your idea, you're thinking. Once it's a theory, you have more than one person, more than people on the same board with that hypothesis.
Yeah, a theory has to be rigorously argued. That is, it has to undergo severe scrutiny. People can come up with hypotheses, but hypotheses don't have to stand up to rigorous scrutiny. You know, anybody can propose it, but once you have a theory, then it should have been already tested rigorously. So this is just a hypothesis, you know, thinking about, this is superoxide here. This should be a negative. A lot of MD people, they don't pay attention to the charge. This drives chemists crazy because the charge makes such a huge difference. You know, whether there's a negative charge or no charge, that's a huge difference. And so one of the things that he mentions, well, if this hypothesis is correct, then you want to take some antioxidants. Antioxidants like what I talked about the other day, N-acetylcysteine, which is similar to antioxidants your body uses to get rid of superoxide. You know. But oxidative, this hypothesis is oxidative stress. You know, there's oxidative stress from these oxidizers. Oxygen wants how many electrons? Two. In superoxide, it doesn't. And superoxide is weird because it only has one. So this is talking about, this is update 83. He has multiple updates on this hypothesis. Vitamin D and oxidative stress. COVID. And so all we need to do is add more oxygen. If we add more oxygen, we should be able to get this. And so what is your argument against CO3? Because I propose CO3 should be fine. Just open the barrel a little bit more, allow more air in there, and we'll get CO3. And so the argument against this, and this is why we're doing this. You know what the pattern is? Oxygen wants to gain how many? 2. So in carbon monoxide, if oxygen gains 2, then what does that mean for carbon? Carbon must have lost lost 2. And so we'll call that carbon 2 plus. Is that okay? Well, what does carbon want to do? So let's take a look at what carbon wants to do, not just what oxygen wants. So we're going to go back over here to the periodic table. If I'm carbon with 6 electrons, I either want to gain 4 to be like neon, that's 10, or lose 4. So carbon's kind of weird because it's right in the middle. It can gain 4 or lose 4. And then it'll be happy because this number of electrons is special. These are for the nerve of noble gases. And the number of electrons turns out to be critical in the theory of chemistry. But losing 4 is a lot of electrons to lose, you know? Each electron requires work to take it. And so losing 4 is very high charge, and so difficult. Sometimes it's difficult. And so in this case, what we say is the range of oxidation states for carbon varies from +4 all the way to -4. So in this case, it's +2. It's not all the way there. It could lose 2 more. Though, okay, it could lose 2 more when you add some more oxygen in there. Take the remaining 2. So it loses 2 more, and then we're going to have 2 oxygens at -2. And that means carbon is
+4.
+4. +4 is a very difficult charge to get. And so this is why we call it the apparent charge. This is for bookkeeping. So oftentimes we don't write +4 like this. Oftentimes we'll just write it in Roman numerals to indicate that that's kind of the oxidation state, the apparent charge versus the charge. So this would be carbon +4. If I form carbon trioxide, what would it be? Well, I have 3 oxygens. Each oxygen wants to gain 2, so that's going to give us -6. That means carbon must be +6. Now, +6, is that an expected charge for carbon? Or expected oxidation state for carbon? You know, so if it loses 4, it's like helium. And then once you get to helium, you don't want to overshoot it, right? You're going to stop there. So the argument against this is, no, we're going to stop at +4. +4 is what we call the max oxidation state. So this is the max positive oxidation, this is the max negative. So we have this range, and this range is what we expect for carbon. The range is based on the pattern of the periodic table. Does that make sense? And so we can see, you know, carbon trioxide, nah. What about if I have 4? Do you know what they call 4? 3 is tri. 4 is called tetra. So carbon tetraoxide? No, this would be +8. How many electrons does carbon have? 6. How can you lose 8 electrons if you only have 6? Well, this doesn't make any sense at all. That wouldn't work unless it's a peroxide. If it's a peroxide, then that screws things up. But we're assuming it's not a peroxide. It's not like hydrogen. And so CO2 is what we call completely combusted. In other words, completely oxidized carbon. And so it's going to stop. This is complete because we aren't going to go beyond +4. So this allows us to make predictions easily. So when we burn carbon, we form these. These are the oxides of carbon, monoxide and dioxide. What if we burn nitrogen? There are different ways of burning nitrogen. The element nitrogen is extremely hard to burn, for one. You know, nitrogen doesn't want to lose electrons. When burning, we have oxidizer and we have fuel. Nitrogen is not a good fuel. It doesn't really want to lose electrons. Good fuels are like the metals. Can you burn metals?
Yeah.
Yeah, metals are flammable. You know, I told you about the steel wool. Mm-hmm. Metals are good fuels because they have electrons that the oxidizers can take without too much difficulty. Nitrogen, no, it holds onto its electrons pretty tightly. But it is possible to burn it like in diesels. And so what kinds of oxides of nitrogen would we expect to form from diesel emissions, sometimes car emissions too. Well, what kinds of oxides of nitrogen would we expect to form? Well, one of the oxides, this came up this morning, is nitrous oxide. Yeah, you could form some nitrous oxide. That wouldn't be so bad because nitrous oxide is called laughing gas, right? And is laughing gas going to kill you? At a certain level, it will. But you know, if the diesel ships and the diesel trucks were emitting nitrous oxide, then probably people wouldn't care so much. You know, maybe people would be happier. You know, I think so. So it's okay. If oxygen had an apparent charge of -2, what would the charge on nitrogen be? So we have one oxygen and we have two nitrogen. So we got a -2 over here, and we need it to balance it as compound, so it's neutral. So we need to balance it by +2. Each nitrogen must be +1. So this is called nitrous oxide. But what are the others? So what are the others? We probably should start thinking about nitrogen. Nitrogen can gain 3, right? Or it could lose 2. It has 7 electrons. So if it gains 3, it has 10. Or it could lose 5 and get 2. So nitrogen's oxidation state varies from +5 to -3. That's the variation. So here I have +1. When it comes to nitrogen versus oxygen, oxygen is going to take it. Oxygen is a better oxidizer than nitrogen. So nitrogen is not going to take electrons, so it's not going to go negative. So we have +1 here. What if we had a little bit more oxygen? If we had a little bit more oxygen, we unscrew the barrel a little bit more oxygen in, what could we form? We could form this one, NO. You know what NO is called? Well, nitrous oxide is N2O.
Nitrogen monoxide?
Okay, that's the systematic name. The systematic name for nitrous oxide is called dinitrogen monoxide. Dinitrogen monoxide. NO is called nitrogen monoxide. That's one name, but it has a common name.
Is it like NOx?
This one is called nitrous, and this else has a counter point, and that would be it's nitric oxide. So this has a historic meaning. The ALS usually refers to the lower oxidation state, and the IC usually refers to the higher oxidation state. So if oxygen is -2, what is nitrogen? Nitrogen must be
+3.
+2. It's a compound, so the charges have to balance out to 0. So +2 -2 balances out to 0. So the IC refers to nitrogen in the +2. The ALS refers to nitrogen in the +1. The IC and ALS don't refer to a specific number. So for example, for some elements, the IC refers to +3, the ALS refers to +2. In fact, that's the most common that we see. In other things, the IC refers to +2 and the ALS refers to +1. It's all relative, and so it's not fixed. So IC is not always +2. Sometimes it's +3, or and the ALS isn't always +1. And so this naming system is better. And the IC ALS only works if there are only 2. But for nitrogen, they're not only 2, they're more than 2. And so nitric oxide is one of those ones that you don't want. And so when you have a diesel engine or even an automobile engines, they're going to be looking for nitric oxide. How much nitric oxide is coming out of your tailpipe? Because you don't want this because this is going to lead to smog. And nitric oxide, you don't want to inhale it. Although, people were inhaling it for COVID. Did you hear? There were a number of medical studies where they used nitric oxide inhalation. Have you heard that? And the reason is nitric oxide. Did you know nitric oxide won Molecule of the Year in science?
Oh, that's nice.
Yeah. In fact, there's a Nobel Prize awarded. Nobel Prize awarded to scientists for nitric oxide discoveries. And in fact, one was the Molecule of the Year. Molecule of the Year was 1990, I think it was. Let's see. I had it up here. 1992. In 1992, nitric oxide won Molecule of the Year. Do you know why? Nitric oxide won Molecule of the Year because it's an important messenger in your vascular system, in the blood system. And so nitric oxide plays a huge role. And so people were thinking this might be one way to lower thrombosis, blood clotting, because blood clotting seemed to be the mode of death for a lot of these COVID cases. And so nitric oxide, they're looking at reducing that, increasing blood flow, and preventing clotting. And I don't know how effective it was for that. But nowadays, you can buy lots of nitric oxide supplements. You've seen these? There are lots of them. So this is Nobel Prize. I'm talking. People thought of nitric oxide as smog, pollution, just associated with negative things, but it turns out nitric oxide is important in your body. We all need some nitric oxide, although not too much nitric oxide, as with anything. And where was that? This is another oxide. I was talking about oxides here. I guess I put it away just to close the tab. Okay. So anyway, so my sister gave me some supplement that boosts nitric. There are others like the classic nitric oxide supplement is Viagra, but they have others that are like for your heart. And so this nitric oxide supplement that she got me is called Cardio Boost or Cardio Miracle, I think it was called. And so it's for your heart health. And so I tried a little bit of that. It's very expensive. But anyway, that's one. But are there more? So I have +1, +2. Can you think of one that has nitrogen in the +3? Because this goes from +5 to -3. So we're starting off at +1. We'll go to +2, +3, +4, +5. So what would have a nitrogen in the +3? Well, that's going to be hard because oxygen is -2. But, for example, if I did 2 nitrogens at +3, how many oxygens would I need? So if I did 2 nitrogens, and 3 plus 3 doesn't really matter. The convention is 3 plus. How many oxygens would I need? 1? No. 2? No. 3?
Mm-hmm.
Yes. Do you see that? And what would the formula for this be? N2O3. And what would we call this? Dinitrogen trioxide. So would it be reasonable to expect the existence of dinitrogen trioxide? Sure, it would be. There's also another one, N2O4, which is similar to this, except everything's doubled. So that's +3. What would be +4? If I had nitrogen in the +4, what would I form? had nitrogen on +4, I would form NO2. Do you know what NO2 is called? Nitrogen dioxide. Nitrogen dioxide is the big one. When you see the brown haze, let's say you go to the harbor and you see the brown haze, that brown haze is this nitrogen dioxide usually, and that's LA used to be full of brown haze. You know, when you had a lot of older cars. Newer cars, you don't see this with catalytic converters. But a lot of catalytic converters being stolen. The catalytic converters just convert this back into nitrogen. So they just reverse this reaction. But this is a toxic gas. NO is a toxic gas. So these two are the big ones, NO and NO2 for smog. But here, this will be nitrogen, and I'm going to write Roman numeral 4 to represent that as the apparent charge for that. So this is nitrogen dioxide. Can you think of a nitrogen on +5? What would that be? So I can't have one. So if I had nitrogen in the +5, I'll use Roman numeral 5. I'd need at least 2 of them. So if I had 2 of them in +5, that would give me +10. How many oxides would I need? 5. And then it would balance out. Because compounds have to be electrically neutral. So we balance this out. And we'd expect this, N2O5, to exist.
Why can't you have one nitrogen? Because I thought the oxidation state range of nitrogen went from +5 to -3.
Yeah, we can have one nitrogen.
Oh, so you could have one nitrogen?
The problem is this. Are you saying like one nitrogen with a +5 charge on it?
Oh, because we couldn't have any oxygen that added up to +5?
No. The reason is because of this. Did I take a break today? Okay, I'll probably take a break pretty soon. But the reason is this. If you want electrons, who's the easiest to take electrons from on the periodic table? The left side and the top or the bottom of the left side? The bottom of the left side. Why? Because they're big. They're big and easy to take electrons from. So cesium is really easy. Taking an electron from it's gone. But what if you have something that's small and actually comparable to you? If you look at nitrogen and oxygen, they both want electrons. Oxygen wants 2, nitrogen wants 3. Both of these are oxidizers. But you can't have 2 oxidizers. Well, you can. You can have 2 oxidizers, but nothing's going to happen. They're going to be stable. So if everybody's an oxidizer, then no reaction is going to happen. What you need is you need an oxidizer and you need a reducer. You need somebody to take and somebody to lose. Both of these want to take, but one of them is going to lose. Which one's going to lose? Nitrogen. Now, nitrogen is going to put up a fierce fight. Nitrogen's going to put up a fierce fight because it doesn't want to lose. And when nitrogen puts up a fierce fight, it doesn't lose all the electrons. So this is why I don't use this. To show that nitrogen really doesn't completely lose all 5, I use the Roman numeral. Apparently, it looks like it's going to lose 5, but it's not. And so what happens is a lot of these oxidation states are stabilized by having the oxygen there. If the oxygen were to leave, just take the electrons and go elsewhere, forget it. It's not going to last. You know, this is going to be too unstable. And so we can't have it alone. It's not going to exist alone. It has to be paired and that's what's going to make it stable.
Oh, that's because it's a diatomic element?
No. You're saying when we do this, the diatomic is when it's by itself. When it's by itself, then it's going to just pair up like this. When it pairs up with something else, then we can change the ratio of that. So it doesn't have to. So the first thing we do with nitrogen is we break this apart. We break it apart into atomic oxygen. And then atomic oxygen, we look in what ratios we can have it. And so this is not nitrogen gas with an oxygen atom. So it's not N2 with an oxygen atom. It's one new molecule, N2O. And so that just so happens to be like that. But over here, we had to break it apart. But also, this one goes N2O4. This is NO or N, oh, not this one, this one. This one here goes N2O4 as well. Although these two are different. Nitrogen dioxide is a unique molecule with NO2. Dinitrogen tetroxide is a unique molecule with N2O4, but they both have nitrogen plus 4. And so this is another oxide of nitrogen that's very common. These can interconvert with one another. So when we make compounds out of diatomics, we always split it apart. And so if you think about table salt, this is the formula I was eating. This was the last time I taught Chem 4. I asked for the formula for sodium chloride. You know what the student gave me? They said sodium chloride is SOCl. But it's not SOCl. What is the formula for table salt? It's NaCl. But then you think, hey, wait, isn't chlorine diatomic? And so some people will keep it diatomic, and they'll call it Na2Cl2. But it's actually wrong. What happens is the chlorine-chlorine bond breaks apart, and then we fix the ratio and mix and match. And so if it's alone, it's going to be diatomic, but if it can pair with the sodium, then it's going to pair like this with the sodium. It'll be happy like that. And so we don't leave it paired because it's found a new partner. And the new partner is going to be happier with that.
So if you have nitrogen with the parent charge of +5, how many actual electrons does it have? The 2? Does it have only 2? Does it have a plus charge? I don't get it, huh?
No, we aren't going to do that because you need quantum mechanics to predict the charge, the actual charge on there, and how many electrons worth it has. What we do is we just use this. This is a bookkeeping method, and this helps us understand this better. So this would be the max. We call this the max. And so if I max out and burn as much of the nitrogen as possible, we get this, N2O5. In reality, though, it doesn't go max because oxygen is not strong enough to pull off 5 usually. And so we end up with like NO and then NO2. This is usually where we end up. These are the common ones. But we expect here, we wouldn't expect nitrogen +6 as an apparent charge. So what would nitrogen +6 be? It would be this. It'd be NO what? NO3. We don't expect NO3 to exist. Why? NO3, even if I just added lots of, this has the highest ratio of oxygen. The ratio of oxygen we can look. What we do is we do this. If we want to look at how much oxygen, it's confusing looking at the formulas and figuring out how much oxygen there is. This one's the least oxidized. It's the least oxidized because if I normalize it and call N1, then O is 0.5. So for every nitrogen, I have half an oxygen there. Here, this is a little bit more. For every nitrogen, I have one oxygen. Here, for every nitrogen, I have two oxygens. Here, for every nitrogen, I have 1.5 oxygens. And so this would be the ratio. And O 1.5. Over here, for every nitrogen, I have 2.5 oxygens. And here I'd have, for every nitrogen, I have 3 oxygens. So this is the most oxidized out of these. But would I expect this one to form?
No.
No, because that would make nitrogen +6. Is nitrogen +6 in the range that we would expect for this?
No.
No. So nitrogen trioxide, no, that's a negative. This is not going to form. And so nitrogen 6 should not form. However, sulfur trioxide is no big deal. Sulfur trioxide is common when you burn coal. Coal contains sulfur, and you burn the sulfur, it forms this, sulfur trioxide. It also forms sulfur dioxide. Why is sulfur trioxide okay, but nitrogen trioxide no good and carbon trioxide no good? And so this is the problem with acid rain. Sulfur trioxide gas and sulfur dioxide gas are bad in acid rain. And sulfur trioxide is okay because sulfur has a oxidation state range of what to what?
Positive 6 to negative 2.
Yeah, positive 6 to negative 2. And so in sulfur trioxide, what is sulfur? Oxygen is negative 2. Sulfur is?
It's positive 6.
Yeah, and then we write this in Roman numeral because losing 6 electrons is hard. We'll write it like that. And so this is fine. What about sulfur tetraoxide? Will we expect sulfur tetraoxide to exist?
No.
So sulfur tetraoxide wouldn't be. How about sulfur dioxide?
Yeah.
Sure, sulfur dioxide, no problem. Sulfur dioxide's common. You know, incomplete combustion is like carbon monoxide. It's not a big deal.
I think I get it.
Are you getting it?
Yeah.
Or not at all? This is sulfur trioxide. Look at Wikipedia for sulfur trioxide. This is what it looks like structurally. Right, so I guess, you know, acid rain isn't that big of a deal anymore. Compared to what it was before. Because I think they're cleaning up, you know, as everything goes along, they're cleaning up the exhaust from coal-fired. Most electricity, I think, on the East Coast is produced from coal. And so they just clean up the exhaust. I had to learn about it when I was a student.
Can we take a break?
Yeah, let's take a break.
Can I ask you a question?
Okay.
Can you go over how you're deriving the min max electron states that each of these elements wants? I didn't really get what you said initially.
I just look at the number. How many electrons does sulfur have? 16. So we want to get to 18 or 10. Because these are noble gas numbers. Noble gas numbers are stable, indicate stability.
But how do we how do we know that like sulfur wants to? How do I know if it wants to get to argon or neon? Like how?
It depends on what you react it with. If you react sulfur with certain things, it loses. If you react it with other things, it gains.
Okay.
And so if you react this with something that sulfur can take electrons from, it'll gain 2. So that if it gains 2, it goes to -2. So, but you have to react it with something. So one of the things that you react with sulfur with is with a metal. If you react sulfur with a metal, you form what are called sulfides. Sulfides will gain 2. They'll be like oxide.
Mm-hmm.
However, if you react sulfur with oxygen, sulfur is not going to gain, sulfur is going to lose. And then sulfur loses because oxygen is smaller than sulfur. Even though they both want to gain 2, there's going to be a winner and a loser. Oxygen is going to be the winner. It's smaller, it's more reactive. So if sulfur loses, how many can it lose? Well, it can lose all the way up to, well, we're at 16. It could lose all the way up to 6 electrons. It's not going to go beyond 6. So what we could have is sulfur plus 1, sulfur plus 2, sulfur plus 3, etc. And so we'll have sulfur in various oxidation states, and those types of compounds we expect. However, there is a preference, you know. So for example, if sulfur loses with oxygen, oxygen is plenty powerful enough to make sulfur plus 4 or sulfur plus 6. Sulfur dioxide is very common. Oxygen is plenty powerful enough to make sulfur dioxide.
Where does the 6 come from? Because you have 16. I'm just not understanding.
Goes to 10.
So what's so special about 10?
What's special about 10, it turns out the number of electrons is going to dictate a lot about the properties. So based on observation, helium, neon, argon, krypton, xenon, these are all stable. They don't want to interact with anybody. They're happy as is. So we got to see that based on observations, there's something making these stable. And what's making these stable is the number of electrons. And so that's the common thread for this. So for example, fluorine wants to gain 1, then it'll have 10. Sulfur wants to gain 2, it'll have 18. But not everybody can gain. You know, if there's somebody that gains, somebody else has to lose because it's a zero-sum game. That is, there's got to be a winner and there's got to be a loser. You can't have both win. So both sulfur and oxygen want to take electrons, but they both aren't. Therefore, there's going to be a winner and there's going to be a loser. Both of them want to go -2. Oxygen wants to go -2, sulfur wants to go -2. But in this case, we can't have that. And so in this case, one of them is going to lose. The one that's going to lose is going to be the bigger one. The bigger ones lose easier. The smaller ones gain easier. So sulfur is bigger, that's going to lose. If it loses, how many can it lose up to? Well, if we're at 16, it can lose 1, we're at 15. Loses 2, we're at 14. Loses 3, we're at 13. Loses 4, we're at 12. Loses 5, we're at 11. Loses 6, we're at 10. Once we get to 10, then it's going to stop there because now we're at
We're in a stable.
yeah, we're at a stable. And these numbers are special, 2, 10, 18, 36, 54.
But it all depends on what it's reacting with.
It depends on what it's reacting with because not everything can take 6 electrons from sulfur. You know, if you had something that's much weaker, then forget it. It's not going to happen. And so if we had something like nitrogen, nitrogen might not take that many from sulfur. And so it depends on what we react in. And so this is why we get a mix. Yeah. So based on that, we can make some predictions like this, based on that pattern there.
So for these compounds, like there's always going to be one element that oxidizes like to the number it wants. Like there's always going to be a winner, so you can't have like
Yeah, unless things screw it up, like not enough hydrogen peroxide. Oxygen wants 2, but there's not enough hydrogen to give it to. And the same thing with like, carbon monoxide. Carbon can give up another 2, but there's not enough oxygen. And so we get these, and so what we end up with is variable charges.
So then does hydrogen peroxide want to decay into water because that's the happy state
Yeah.
for both of the atoms?
Right. And so hydrogen peroxide decays into water. Absolutely.
And that's why they have like the dark containers,
Yeah.
because the light makes it decay, huh?
Yeah, light makes it decay faster. And so what happens with hydrogen peroxide is hydrogen peroxide decays into water, which is very stable, it's happy as is, and oxygen gas. Then we balance it. We'll need 2 hydrogen peroxides here. And we're going to form 1 water. And Let's see, this is not quite balanced. I need to go with 4. Let me go with 4 hydrogen peroxides here. And then they'll give me 2 waters. And 3 O2. So it'll give me 6 plus 2 is 8. 4. Yeah, that would be that. So hydrogen peroxide is known as a powerful oxidizer. You can use these oxidizers to kill bacteria. Like bleach. Bleach is probably one of the best for killing and sanitizing surfaces.
So with the carbon oxides, carbon dioxide is the stablest state, and does
Carbon dioxide is the max, yeah, at the max. Sometimes it's not the most stable. Just because you're at the max doesn't mean you're the most stable.
I looked up on Google and it said that you can make carbon trioxide, but it's extremely unstable and it decays.
It's extremely unstable, and carbon trioxide would have like a peroxide style link. So it'd be an unusual compound. And so that would be similar to a hydrogen peroxide. It kind of screws things up, but yeah. If you look at carbon trioxide, the one on Wikipedia, that is not carbon plus 6. It's not carbon plus 6. That's because all the oxygens didn't get enough. So we might have 2 peroxide-like oxygens and 1 oxide-like oxygen. And since peroxides are very unhappy, but carbon's going to stay at plus 4. It's not going to go beyond. So even though it's carbon trioxide, it doesn't go beyond its max. Its max is 4. And that is what creates this. It's the oxygens that lose out, just like hydrogen peroxide. The oxygens are going to lose out, and that's going to make it very reactive. This is going to be extremely reactive because the oxygens are unhappy.
And that's why it decays so quickly.
Were there any questions? Okay. Is its position on the periodic table going to tell you how many electrons it sheds or gains? Yes.
You've already done.
No. The answer to that is it tells you the range it can shed or gain. But it doesn't necessarily tell you the amount. It depends on what you react it with. And as you get more experience with this, then you'll see that there are some common charges that, for example, if we're looking at group, this is called group 1 or group 1A, or the alkali metals, all these are going to be shedding how many electrons? Just 1. And so the periodic table for sure is going to tell me that this is all these are going to be plus 1. And so examples of that would be, let's go Na plus. We call this sodium ion. To differentiate between sodium metal and sodium ion, we add the word ion. And so we know sodium ion is plus 1 because that's where its position is. So it's going to lose 1 and lose it quite easily. However, magnesium, let's go, or beryllium, we'll skip beryllium. We'll go look at magnesium. Magnesium is always going to be plus 2 in compounds, I'm saying. It could be 0 in the element, but in compounds, magnesium is always going to be plus 2. because it's going to be too hard to gain. Same thing. Sodium is too hard to gain. It's much easier to lose. So for magnesium, we're always going to get 2 plus. In fact, all these will be what we call fixed charge. This is fixed. This is fixed. And so we predict magnesium, calcium, strontium, and barium are all going to be fixed charge of +2. They're all going to lose 2. Now, when we go to 3, we can go to scandium. Scandium is always +3. Scandium's Sc, so this would be scandium ion. This is magnesium ion. This is scandium ion. It's always +3. It's fixed. And this goes for the other elements in the family. And so scandium, yttrium, which is below there, and lanthanum, you see it? This periodic table is not complete. These are all always going to be +3. There's a lot of blanks here. These blanks, a lot of them are unnecessary. Lithium ion, sodium ion, potassium ion, rubidium ion, cesium ion. Calcium, we want strontium here, which is missing, and barium. Scandium, yttrium, meh. Lanthanum, meh. Scandium, maybe. That's +3. And so, if you have a good decent oxidizer, we can get +3. You know, +3 seems to be achievable. And what's a decent oxidizer? A decent oxidizer is oxygen. So oxygen can take up to 3 electrons, usually with no problem. But up to 4 electrons, it's starting to get difficult.
In the fourth column, is that supposed to be 4B?
Yeah. This is supposed to be 4B. So if we go to titanium, it's getting harder and harder because that's a lot of electrons titanium has to lose. Titanium has to lose 4 electrons per atom. Not easy to do at all. And so rather than writing titanium 4 plus, sometimes we use the Roman numeral to indicate that that's going to be hard to do. And so it's going to be the apparent charge. And so titanium is what we term variable charge because we might not get it all the way to titanium 4. You know, we might get it close, but not all the way there. And so for titanium, we start to have anywhere from 0 to +4 for the charge. And so, for example, here, we could have TiO2. TiO2, oxygen is going to be 2 minus, and titanium is going to be 4 plus. Or 4 plus is hard, so we'll just call it 4. That's the apparent charge on that, right? But we could also have TiO. TiO would be, yeah, this would be like titanium dioxide. It's a paint pigment. This would be titanium monoxide. It might be hard to get it all the way to 4, right? There's a lot of electrons to lose. And so we start to get into what's called variable charge.
So would that be +2?
Yeah, this would be +2. So, so what we call this ion, we're talking about ion. This ion is called titanium Roman numeral 4 ion. And this ion here would be called titanium Roman numeral 3, or no, Roman numeral 2 ion. So we have titanium 2, titanium 4, possibly titanium 3. You know, titanium 3 is not as common as titanium 2 and 4. But it's certainly a form. Titanium 1, yeah, but not as common. You know, those are rare. But we'd expect everything from titanium 0 would just be titanium metal. And so when we have variable charge, we name it different. Scandium's always +3, so we don't need a Roman numeral. Sodium's always +1, so there's no sodium Roman numeral 1. But when we start getting at these high charges, it becomes difficult to oxide. So the next variable charge would be, after titanium, would be vanadium. Vanadium can lose up to how many? Max. So if I look at vanadium, 5. If I lose 5, then it'll be like neon. Vanadium's 15. Yeah, so lose 5 will be 10. Thanks. Is that right?
It would be argon, right?
Argon would be 18. So vanadium would be 23. Is that right? Yeah. 23. And so losing 5 electrons is not easy. So we expect variable charge, And so the charge can be anywhere from 0 to plus 5. And so we're going to have that. These are variable charge. In fact, all of these are variable charge here because it's getting harder and harder. After vanadium comes chromium. Chromium can go all the way to plus 6. That would be the max. In fact, you can see the max here. Do you see this Roman numeral? That's the max. So after chromium comes manganese. And manganese can go all the way to plus 7. And then after manganese comes iron, cobalt, nickel. Iron, cobalt, nickel are grouped together. So iron, cobalt, nickel. And you'd expect 8, 9, and 10, but we don't see it. It tops out at 8, pretty much. Getting a parent charge of 9 and 10 is just practically non-feasible. And so it's topped out here. And so this is why you can see. You see this? 8B is topped out. And then a weird thing happens. When we go from nickel, we go to copper. And you think, oh, copper is going to top out at 11. No, it doesn't. You know what copper tops out at? It crashes back down to 1. So the max on copper is 1. Actually, copper bucks the trend. Copper doesn't play by the rules. And so the max on copper is 2, but it's unusual because right below copper is silver. So copper is variable, but silver maxes out at plus 1. And so copper, we have copper plus 1 and copper plus 2. And next to copper, we have zinc. Zinc maxes out at plus 2, and actually there's only 1 charge. These are easy to generate. And we have cadmium. These are fixed charge. And so there's a little island of fixed charge. The rest of this is green. Green just means variable charge. And so who knows what that charge is going to be? Unless we're in this little island here. In this little island, we have fixed charge. Silver is always plus 1. Cadmium is always plus 2. Zinc is always plus 2. Copper is variable charge, so we have to indicate which charge is it. Copper likes plus 1 and plus 2. And so this is going to be a lot, probably, but basically the common charges up to copper, I know I could go up to pretty high, but the common charge for these species is plus 2 and plus 3. So most of these like to be in the plus 2 to plus 3 range, not their max. When I get to over here, we're plus 1 and plus 2, and then, out here I have, let's say, plus 1 and plus 2. Mm-hmm.
Is column 4, is that also part of like the green section? Or?
Over here?
No, the 4.
Oh, yeah. This is also variable charge. So titanium's variable charge, so we have to, when we say it. So let's look at 2 common chromium. Chromium can go all the way to plus 6, but it's going to be unstable. If it's monatomic, it has to be alone. If it's alone, it's probably not going to get all the way to 6 because there's too many electrons to lose. And so for chromium, plus 2 and plus 3 are the most common. So chromium plus 2 is called the chromium 2 ion. Roman numeral 2 ion. Chromium plus 3 is called the Roman numeral 3 ion. So this is Roman numeral 2, chromium 3 ion. And so most of these are plus 2, plus 3. Over here we'll have plus 1, plus 2, and then we have some over here that are variable charge, like tin. You know, tin is +2 and +4 is the most common. The max, though, is higher. For tin, the max is 4. Actually, I'm offset here. Tin, the max is 4, but +2 and +4 are quite common. Lead is the same thing. Lead, the max is +4, but +2 and +4 are common for lead, etc. And so these are variable charge. So if I have tin +2, I call it tin 2. If I have tin +4, I call it tin Roman numeral 4. Lead is variable charge as well. Now there's a jump here. So we can go from 2A to 3B, or we can go from 2A all the way to 3A. And so going from 2A to 3A, we go magnesium to, what's this? Boron. This would be aluminum. So we go from magnesium to aluminum here. Actually, I'm one out. Sorry. Magnesium 2+. If we go to magnesium to aluminum, aluminum has 13 electrons. So if we're at 13 electrons for aluminum, then we can lose 3 to get to 10 electrons like neon. The periodic table is not complete. So this is fixed. Aluminum 3+ is fixed. And pretty much the rest of these are variable. Variable charge.
Doesn't seem very organized. The table, just the pattern, just the natural pattern. They have groups, but
It's not predictable.
yes, it's hard.
I don't think it's meant to be organized by this attribute, right?
The periodic table? No. No, not the periodic table. Oh, I'll show you where you'll see a pattern. Maybe a little bit easier to see pattern. If we're talking about monatomics, like carbon can go either way. But carbon losing 4 electrons is going to be quite a struggle. And so normally, if we think about carbon would rather than losing, although it could lose, it could gain. How many electrons can carbon gain?
Carbon can gain
4.
Yeah.
And so if we have to take it from something that's very easy to take electrons for. So if we have carbon with 4 extra electrons, we call that carbide. And so things turn here. To the left of carbon, it's probably easier to lose. At carbon and to the right, it might be easier to gain. And so carbon with a 4 minus is not called the carbon ion. It's called carbide ion. And then nitrogen would gain 3. This forms nitride. And then oxygen gains 2. This is what it likes. This is the favored charge. We call it oxide. And fluorine, gains 1, and we call it fluoride. And so what's common for all these are all fixed charge, although we could have variable charge. You know, carbon can have anywhere from +4 to -4. But these are the common ones for gaining here. Fluoride, chloride, bromide, etc. Oxide, then below oxygen is sulfur. And so I was talking about this earlier. Now, both oxygen and sulfur want to gain. How many do they want to gain? 2. So oxide wants to be like this, and sulfide wants to be like this, but unfortunately, both can't gain. One has to gain, the other has to lose. And so in this case, if we react oxygen and sulfur, oxygen gains because it's smaller, and sulfur loses because it's bigger. And then we form things like sulfur trioxide, in which we're going to go sulfur plus 6. And so we'll have that variable charge. These are the fixed monatomic ions, and most of these we can get from the periodic table. The pattern that we remember is just the number. If you can look at the number and see how many it wants to gain or lose, then we can kind of figure it out. And then if we remember that the negative charged ions, which are called anions, have the I ending, then we're okay. And the positive are just the name of the element. And we got to know if we're in the variable charge, because that's going to tell us if we need a Roman numeral or not. Okay, the next series of ions we're going to look at are the polyatomic. The polyatomic, some of these you're just going to have to memorize. And the way I memorized, actually the way I memorized all, you know the way I memorized all these when I was a student? Initially I tried flashcards. But the problem with flashcards is when it came to writing, I couldn't remember. Was that charge 2 or 1? Or how many, what was the ratio again? I couldn't remember it. And so flashcards didn't work for me. I didn't do so well. And then what I did was I wrote them over and over. Do you know how many times I wrote the difficult ones, like before the test? Like the really hard ones to remember, I wrote hundreds, maybe 500 times. I just wrote it. And the purpose of that was to get it into my motor memory so that when it came to the exam, I just write it without thinking, you know, it's motor memory. But you might think, well, that might be easier than all this stuff, you know, just flashcards or writing it over and over again. But the problem with that is, if you have something that's not in the book or was never talked about in lecture, then you've never made a flashcard for it, and you've never written it down. But if you have a pattern, even though initially may seem like more work than just trying to memorize it, is actually going to be more beneficial because you can make some predictions with it. Some of these, there's no pattern to it. You just got to memorize it. So if we look at polyatomic cations are spelled like this, and they're positively charged species. So some common polyatomic cations would be like this: ammonium ion is NH4 plus. We have mercury. This is called mercury 1 ion. Mercury 1 ion is He2 2 plus. That's 2 mercuries with total positive charge of plus 2. This is versus mercury 2. The He2 plus is called mercury 2. But it's not polyatomic, this is monatomic, in which each mercury, there's only one, has a plus 2 charge. And so polyatomic ammonium, mercury 1 cations would be, the other one would be H3O plus. This is called hydronium ion. A lot of these polyatomic ions come from geology, minerals. And we have the polyatomic 8s. These are anions. Anions have a negative charge. And historically, the 8s, we live in an oxidizing atmosphere. Air consists of 21% oxygen. And so things tend to get oxidized. And so when we're looking at the 8s, a lot of these come from mineral deposits. You've got oxygen, maybe it's been fully oxidized. And so one of these would be like boron. Here. Boron forms borate. And so we have borate deposits, let's say. And these borate deposits are going to have this borate in them. Borate is an ion that has 3 oxygens with a 3 minus charge. Boron is in group 3B, or 3A actually. So it's in group 3. And so the easy way to remember borate is 333. Group 3, 3 oxygens, 3 minus. It's borate. What's the max positive charge of boron? Plus maybe I need the other periodic table up here. Boron has 6 electrons, so it can either gain 4 or lose
4. No.
Oh, sorry, it's not 6, it's 5. misread that. It's 5. So if you either gain 5 or lose 3. So plus 3 is its max. Well, if it's boron versus oxygen, oxygen is going to win. So that's minus 6. And that means boron must be, so this is minus 6. Minus 6 plus what gives us a net charge of minus 3? Yeah, and so this is plus 3. And so the 8s usually refer to max ox. Max oxidation. That's what you expect. In minerals, you expect them, they've been surviving in this oxidative atmosphere, you expect them to be maxed out. And so borate's maxed out, max oxidation. Oh, let me put a little asterisk here, except for some. There's an exception to that. And so carbon's been around for a long time. And so we have CO2, but we also have minerals that contain carbon that have been maxed out. One of the minerals that contain carbon that's been maxed out would be carbonate. And so this 8, the T refers to an oxyanion, T. Versus carbide. Carbide is what we call monatomic anion, carbide. And so usually when we have the D, that typically is monatomic anion. There are exceptions to this. And so the T, that's telling me there's oxygen. And so do you know what the formula for carbonate is? It's CO3 2 minus. That's it. And is carbon maxed out? What is the max positive on carbon? Plus 4. And so carbonate, well, we have 3 oxygens, is minus 6. Minus 6 plus what gives us minus 2? 4 plus 4. This is maxed out. So carbonate's maxed out. So geologists study carbonate. Well, there's lots of carbonates on Earth.
When you carbonate your soda, is that the same thing?
When you carbonate your soda, yes and no. Yeah. When you carbonate your soda, there's something carbonic acid. Remember that? And that has carbonate, but what ends up happening is you generate CO2. In fact, this is one of the things that people are looking at for CO2 capture is converting the CO2 in the atmosphere into carbonates. And there's a lot of work being done. This is why they're saying, you know, I think they're saying like some of the coral reefs are actually increasing in mass. Have you heard that? Because maybe the CO2 concentration is going up and providing more CO2 to form more carbonate. See, coral reefs are made up of carbonates. So that's boron, carbon. What comes next? Nitrogen. And so we have nitrate. You know what the formula for nitrate is? NO3 minus. And then let me speed it up here. Then we have oxygen. There's no oxide. There's, you know, oxygen taking from oxygen is not going to happen. And then we have fluorine. And we'll have fluorate. Fluorate is FO3 minus. Do you see a pattern? What do all these have in common? 3 oxygens. And do you see a pattern in the charge? Yeah, it goes 3, 2, 1, 1, 1. We stop at 1. So that's fluorate, and then we have chlorate. Chlorate is ClO3 minus, and then we have iodate. Actually, I forgot bromate, sorry. We have chlorate and then bromate, which is BrO3 minus, and then we have iodate. Iodate is IO3 minus. And I said, in geology, this is maxed out. You know, these things have been around, they've been oxidized completely. So what's the oxidation state of nitrogen here? Nitrogen would be, okay, so 3 oxygens and minus 2, that gives us minus 6 plus what gives us minus 1? 5. And so this is going to be plus 5. That's maxed, right? But when we go over here, what's the max for fluorine, chlorine, bromine, iodine? Positive. What's the max positive? Plus. Chlorine varies from plus, well, we're at 17, so if we lose 7, we're at 10. So chlorine varies from plus 7 to minus 1. Chlorine for sure prefers to be minus 1. That's the easiest, right? But this one, do you know what it is? Chlorate? If we look at chlorate, we have 3 oxygens. Each oxygen is minus 2. So that gives us minus 6. Minus 6 plus what gives us minus 1? This has got to be plus 5. So plus 5 minus 6 gives us minus 1. Is plus 5 the max?
Yep.
No, actually the max is plus 7. Yeah. So the origin of the 8 comes from historical analysis of minerals, that kind of thing. But the minerals that were found to contain these were the species here, let's say. The max is actually one step farther. And so what we had to do here was, this isn't maxed out. The reason it wasn't maxed out is because it's too hard to get it to plus 7. You know what we need to get it to plus 7? We need one more oxygen. And so if we go one more oxygen here, so we go ClO4 minus, then that's one more step above. You know what we're going to call this? This is chlorate. You know what we're going to call this? You know, like this would be the hyperactive version of chlorate.
Oh, what's the
hyperactive? You know what hyper means? Means maybe overly active. But we're not going to call it hyper. We're going to drop the high and just call it per. This is called perchlorate. Perchlorate is terribly unstable. And so this is why it wasn't found, because it's kind of unstable, because the chlorine is all the way at plus 7. Would you expect to find hyperchlorate? Would that be something you would expect to find perchlorate? No, because we're already maxed out. This is the max. And it's very reactive, being that. And so this is kind of where they thought the max was, but it turned out to be wrong. The max went a little bit farther. But by that time, they had already named this the 8. Since they already named this the 8, then they had to call this hyperchlorate, or just perchlorate. Does that make sense? The same thing happens with these other ones as well. Okay, now what we're going to do is this. Normally, I just memorize one. I already memorized these as a student. So. But if I were redoing this, I just memorize borate. Borate's group 3 has 3. It's easy to remember, and then memorize the pattern. That way I know all of them. However, something happens with the pattern when I get to silicon. If I go to silicon, you know, I have carbide, I could have silicide too. Silicide would just be Si4 minus. But I could have silicate. And so silicate is actually SiO4 4 minus. Geologists like silicates, the silicate minerals. And so the way we remember this is silicon is in group 4. So it's 4, 4, 4. And so the two anchors here is you memorize borate and you memorize silicate, and then you can figure out the rest. Because if I know what silicate is, then next to nitrate and silicon, nitrate and silicate is going to be arsenic, or no, phosphorus. And so over here, I'm going to have phosphate. And so like silicate, phosphate has 4 oxygens, but the charge is different. The charge on phosphate is 3 minus, so that's phosphate. And then below oxygen is sulfur, so I'll have sulfate. And sulfate is SO4 with a 2 minus charge. So do you see what all these have in common? 4 oxygens. Do you see what the charge is doing?
432.
Yeah, 432. Now, this is where it kind of gets a bit confusing, so you have to memorize the pattern. Below phosphate is arsenic, and that makes arsenate. Arsenate is ASO4 3 minus. Below sulfur is selenium, and so we can form selenate. Selenate is SeO4 2 minus. So if selenate is SeO4 2 minus, what do you think tellurate is? Tellurate is below selenate. Tellurate would be, well, this is sulfur, selenium, tellurium. What do you guess? TeO4 2 minus. So it's kind of weird, you know? And so there are two patterns. There's the outer pattern and then the inner pattern. And so if you memorize the outer pattern and the inner pattern, you're fine. You can generate a lot of ions here. Once we have these patterns down, then we can derive a lot of other ions based on this. So I don't have to do very much memorization. I'm trying to minimize the amount of memorization. And so the other type of anions that we have are the ones that end in ite, the ite ions. Most of the ite ions are this: one less oxygen than the 8, same charge. Okay. So one less oxygen. So that, let's look at nitrate. Nitrate is NO3 minus. What is nitrite? If nitrate is NO3 minus, then nitrite is one less oxygen, NO2, same charge, NO2 minus. That would be nitrite. Not everything forms nite. Sulfate is SO4 2 minus. What is sulfite? So when I'm thinking about sulfite, then I got to think sulfate. Sulfate's in this inner block, so it goes 4 oxygens, charge goes 4, 3, 2. So that would be sulfate. Sulfite would be one less oxygen, so that would be SO3, same charge, 2 minus. That would be sulfite. And then we have these others. We have the hyper or the per 8, and then the opposite of hyper is hypo. And so we have the hypo 8s. The per 8s have one more oxygen than the 8. One more O than 8. Same charge. The hypoites have one less oxygen than the ites. Same charge. And the classic example is this. Chlorate is ClO3 minus. And so this is chlorate. And then perchlorate was ClO4 minus. That's perchlorate. And then chlorite is ClO2 minus. And then hypochlorite, which is bleach, hypochlorite, is ClO minus. So that's okay here. So we go sulfite. What about persulfate? Does persulfate exist? Persulfate. So let's try it. If that's sulfite there, and then sulfate is SO4 2 minus, then what about this? SO5 2 minus. This would be persulfate. Would you expect persulfate to exist? It boils down to the charge on this. Each oxygen is 2 minus. We have 5 of them. That's going to give us minus 10 total charge. We have 1 sulfur. That's going to be plus blank, and this has got to equal 2 minus the net charge. And so the sulfur must be plus 8. Is plus 8 okay for sulfur? Is that in the range? No. So we aren't going to form, persulfate does not exist. Now, the per is only going to happen for the halogens here, because these, they thought 8 was maxed out, but 8's not maxed out. For all these others, 8 is maxed out. You know, you can't go any more than 8. But,
What does the halogen mean?
the halogen is just the family name for fluorine, chlorine, bromine, iodine. Those are all called halogens. There are others that we can just derive. These are called acid anions and acids. So we were talking about carbonate earlier. So we have carbonate. If you add, acid is H+. An anion has a charge, negative charge. An acid is neutral. So if you have a carbonate and you add 1 H+, what we form is something called HCO3 with a negative charge. So this is 2 minus plus 1 gives us minus 1. If this is carbonate, then this is called hydrogen carbonate ion. This is carbonate. If we add 1 more H+ to this, then we form H2CO3. H2CO3 is not an ion. There's no charge, it's neutral. And so this is what we call an acid anion. This is an anion, and this is an acid. So if I want to name the acid, what I do is I drop the 8 and replace it with ic acid. So this is called carbonic acid. So it's taking carbonate and then changing the ending to ic acid. That's what we do for 8s. What we do for ites, carbonite is not common, but something like nitrite is common. This would be nitrite. And if we had an H+ here, we don't form an acid anion. If we had an H+ here, it goes all the way neutral. And so we form HNO2 because it's going to neutralize that single negative charge. And so if I have nitrite here, what I do is I change the ending. And so if I have an 8, it's called ic acid. If I have an ite, it's called nitrous. In this case, aus acid, nitrous acid. And so I add the aus acid ending here. If I have an ide, the anions are either going to end in ate, or ide. And so let's go with Cl minus. Cl minus is called chloride. And if I have an H+, I'm not going to form an acid anion because it's going to neutralize everything. It's going to form HCl. And so if I have an ide, what I do is I change it. But I change not only the ending, I change the beginning. And so this is going to form hydrochloric acid. And so I change the beginning to hydro, the ending to ic acid. And that tells me I have the I here. What time do we go till today? 4:20. Oh. Okay, so let's take a look at some more examples of this. So if I have sulfate, I add one H plus, I form HSO4 minus. So this is sulfate. What do I call this? Hydrogen sulfate. Ion. Now, these acid anions have a common name too. And they're usually common names given by bi. And so this is hydrogen carbonate, which is also equal to bicarbonate. In fact, bicarbonate is probably more common than hydrogen carbonate. And the same thing here, this isn't as common as its common name. The common name for this is called bisulfate. It's quite common. If I add another H plus to this, then I'm going to form an acid, which is neutral, H2SO4. What's the acid name?
Sulfuric acid.
Sulfuric acid, correct. Yeah, that's good. Sulfuric acid. So, what I'm going to do is, okay, we're going to do a lot of examples of this, but there are others to memorize. And these, there's no real pattern to memorizing. There is some, when you look at the structure of these. But others to memorize are going to be other ides. Normally when you see an ide, it's monatomic anide. Normally, monatomic anide. And we can get the charge, like for example, chloride. We can get the charge off the periodic table. But there are some others that we just need to memorize. The others that we just need to memorize are like this. We saw this one earlier today. This one's called peroxide. And it's when we have two oxygens. These two oxygens are actually bonded together. Sometimes they can be alone, but these don't like to be alone. They like to pair up like this with a 2- charge. It's hard to tell if they're paired up or two individual ones, but this is paired up. This is called the peroxide ion. This one's not so great. This one's cyanide. Peroxide, cyanide. This one causes a lot of eye damage. This is called hydroxide. What else do we have? Cyanide, peroxide, hydroxide. Maybe it. Okay, the eights. There are some eights that aren't on the periodic table that are easy to see a pattern. Some of these eights are like oxalate. Oxalate, you just memorize it. 242. C2042 minus. Oxalate. Acetate. The way I memorize acetate is 232 minus. I just kept doing it. I wrote it a bunch of times, but this is one I memorized from flashcard. 232 minus. 232 minus. Just kept reiterating that. Acetate. Chromate. CrO4 2 minus. That seems kind of to fit the pattern. But we have another one called dichromate, which is Cr2O7 2 minus. Chromium's maxed out at +6. Both of these have chromium 6. Chromium 6 is the main subject of the documentary film.
Is that the Brockovich one?
Aaron Brockovich, right? Chromium 6. Both of these are chromium 6. Both of these are carcinogenic. Permanganate. is MnO4 1 minus permanganate. The way I remember these, let me tell you how I remember these. Chromium 6, manganese. What's the max on manganese? Manganese 25 electrons. Wants to get to 18. 7. You know what the charge on manganese here is? We have 4 oxygens. 4 oxygens is -8. -8 plus what gives us -1? It has to all add up to -1. Plus 7. Plus 7. What's the max on manganese? Plus 7. So if I forget something like this, how many oxygens was that? Was that 3 oxygens? Was it 4 oxygens? If I tried to make it with 3 oxygens, does it work? And then the charge, we have multivariable, so this makes it difficult. And so one thing you can be sure of is if both of these are +6 and this is +7, then if you got +6 and +7, then maybe it's correct, depending on the net charge. So we got oxalate, acetate, chromate, dichromate, permanganate. I think those are the big ones that we worry about here. And the others we don't worry too much. There are others, but the last category are the thio. Do you know what thio means? It means sulfur. So it means replace 1 oxygen with S. So if we have sulfate, then thiosulfate is what? Well, we'll replace 1 oxygen with a sulfur. So rather than having 1 sulfur, we're going to have 2 sulfurs. But rather than having 4 oxygens, we're going to only have 3 oxygens. So we replace one of the oxygens with a sulfur, and sulfur and oxygen both want to do the same thing. So we end up with a 2 minus, same charge. So this would be thiosulfate. We have a whole bunch of others. Other ones that aren't as common, like cyanate. Cyanate is CNO minus. Thiocyanate is CNS minus. But this one I'm not going to bother. You guys remember that. All right, so this is a lot of memorization to do. Yeah, so I'd get started on these as soon as possible.